Good evening. Thanks for making a very short tea break from Nirmana team. Now we have got a last technical talk regarding fiber reinforced concrete low carbon lining by engineer Benoit Rivas. He is a global technical manager, underground solution. Now we request engineer Benoit sir to deliver a presentation. 1 second, sir. I will tell. You can make a slide show. It's not in a presentation mode, sir. Yes, sir.
Okay.
Yeah, now it's in presentation mode. Just 1 minute, 2 minutes, sir. Yes, sir. You can start the presentation. Once again, from Nirmana team, we'll welcome you, sir, from here. Thank you. Yeah, please, you can start a presentation, sir.
Okay.
Presentation time, it will be 45 minutes. You can have a presentation.
Okay. Thanks. So good afternoon to all. Good evening. Thanks a lot for the invitation. Thanks for the organization of such event, which is very powerful, very useful to share experience, share state of the art. So I will be very pleased to give this lecture this afternoon. The topic is build sustainable precast segment lining with fiber reinforced concrete. As to complete a few words of introduction concerning myself, so I'm Benoit de Riva, working for Bekaert, which is a global company headquartered in Belgium, and we are involved in many activity on two key part, which is the drawing and the coating, and well, so we are involved in automotive, in the agriculture, and also in the construction industry, in building product. And myself, I have a clear focus on underground. So I'm following this activity since more than 20 years with Bekaert. And before that, I was working also for a French contractor, Vinci, as well in underground. So it's a long underground background. So today I will touch the two aspects, mainly when we talk about precast segment, the structural requirements, but also the low carbon requirements, which are more and more important today as clients in their specification are looking for solution with the less carbon footprint. And just to explain current sustainable development concerning the low carbon lining, and a few words of conclusion. It's okay, you can hear me, there is no issue. Yes. So the assessment of concrete lining requires the definition of both the sustainability index and the mechanical index. We have, in the meantime, to bring the structural safety and to meet also the sustainable development requirements. This is really in line with the main United Nations statement, looking for development that meets the needs of the present without compromising the ability of future generations to meet their own needs. So we are today all convinced on this key challenge for underground activity in the future. We know that we use more and more fiber reinforced concrete for precast segment. This is no more an exotic solution. I think the state of the art is quite well summarized by the FIB Bulletin 83 that I could summarize as mentioned on this slide. First, durability advantage at final stage, cracking control during the construction phase, higher impact resistance, boosting the production process, reduction of cost, and sustainability advantages. And this point should be better underlined today, and we're still moving more and more to low carbon solution. I say it's not an exotic solution because we have already more than 40 years return of experience with 200 big projects worldwide in different industry for metro, railway, road, utility project in different places in the world, in US, in Europe, in Asia, in Australia as well. All these projects have provide a detailed return of experience. We have seen that with precast segment, one of the main difficulty when we use traditional reinforcement is during the installation process. You know that bursting in segment occur from two different types of load. In place force, due to the compression in the ring, and mainly during the installation by the application of ram loads to the edge of the segments. The fact there is the minimum concrete cover requirement for corrosion combined with the particular edge shapes leads to vulnerable part of the segments. Spalling at joints will happen quite often, and that means repair must be made that ensure the long-term durability. So the question is, how long will you guarantee this repair? This is the main reason why we have included year after year fiber reinforced concrete inside the segment, because you have fiber in the all direction. You have also fiber close to the surface, and this help to avoid this risk of spalling during the installation of the segments. This is one return of experience from a big project in UK, CTRL. It's part of the high-speed highway between Paris and London. 260,000 segment cast, and just 0.8 rejected during the manufacturing process, and just one major repair during the construction process. So this is a survey from the clients saying that fiber reinforced concrete is really appropriate to avoid this risk of spalling and to maintain the durability of the segments. Manufacturing with steel fiber today is a well-known technology. Fiber are, as you can see in this small video, distribute in a homogeneous way in the concrete mix in the three direction, and we have a different system available today to control the fiber dosage and the fiber orientation. So to summarize in few words the current voice of the designer, you need to deal with ground loading, handing, bolting, erection, ground pressure, or arm loading. All these load case could be taken in charge with the fiber reinforced concrete solution only. And we still have a problem when we use rebar for the ram loading. Saying that, I have to add that the fiber reinforced concrete only is possible by selecting a static system for the tunneling ring in such a way that there is a minimum stress for bending moment. Very high bending moment could conduct to a combined solution when we use rebar for the ULS and steel fiber for service limit states. On the list of reference we have, I will say today is 70% is fiber reinforced concrete only and 30% is combined solution. Steel fiber plus rebars. Well, this was just a few words of introduction to summarize very, very quickly the the current state of the art. Now I will move on the structural requirements. I think the main document today is the Model Code 2010. This document has boosted the acceptance of fiber reinforced concrete by providing a very clear design principle. And this document is included in all the new guidelines produced by different tuning association or committee focus on fiber reinforced precast segment. You have from AFTES, which was the first one. It's also based on the Model Code. In 2016, two documents have been produced by ITA, one from Itatech on design principle, one from the ITA Working Group 2, more focus on lesson learned from the last 20 years. In 2017, there is also a very detailed design recommendation published by the ACI, American Concrete Institute, and also by the FIB, Fédération Internationale of Bâtiment, the FIB Bulletin 83, which also refer fully on Model Code. And since you have also a new document from ITA focused on a more practical issue, how to cast the concrete mix design, etc. And you have also a new document from the ITA Working Group 2. By this slide, I just want to show you that the state of the art now is very well documented through all this document endorsed by high international technical committee. And all these documents could be downloaded from different websites free of charge. The Model Code, so the Model Code published in 2012, it's a pre-normative, it will be part of the future Eurocode. Fibers are included in Model Code, which is the base of the future Eurocode expected in the coming years. From that, there is this precast tunnel segment in fiber reinforced concrete state-of-the-art report published by FIB. I really recommend this document as is a clear guidelines on how to characterize fiber reinforced concrete material performance. You get inside a clear state-of-the-art and a clear design principle. I will not go through in detail today because it should take, I say, one session by chapter, but you have one chapter on the material, how to get the material property, one chapter on the different load case, transition state loading condition, the TBM truss, which are very often the critical load case, the final state loading condition, the fire design, the connector, and the detailed and comprehensive state-of-the-art on durability, and a clear quality control process. On top of that, this document was the first to introduce as well some sustainability index. So you see, it's a very, very complete document that I recommend for all contractor, designer, interesting to evaluate and to promote the fiber reinforced concrete solution. And you have also some case study to calculate the envelope at ULS, at SLS, the stress-strain relationship for nonlinear analysis, and the list of reference of 200 reference. Just a few words on the design flow. I think the starting point, which is when you want to design about fiber reinforced concrete, is to get and to define the relevant material property. And this could be determined using a beam test according to the EN 14651. You can define the performance class and your material requirements. So from the material characterization, you move to the material behavior with the constitutive load, the safety factor, or other impact factor according to the Model Code, to the acting load situation as the molding, stacking, transport and placing service, to the resisting load, bending moment capacity, shear capacity, resistance against spalling, resistance against impact. First step, it's really the point of attention is how to get the relevant material characterization of the fiber reinforced concrete mix. So as I mentioned, the most relevant standard, which is accepted worldwide and for which there is a scientific consensus, is the EN 14651. This is a 3-point bending test with notch. The notch is to control the crack and to give also the possibility to measure the crack opening in a good way. From this test, you have a curve, the load deflection curve, and two main values. The first value is named FR1 characteristic. And this FR1 characteristic is the residual strength for a CMOD of 0.5 millimeter. It's a residual strength for the crack move opening displacement of 0.5 millimeter, which is considered for the service limit state. You have another value named FR3, which is the residual strength for CMOD crack move opening displacement on 2.5 millimeter, which is used for the ULS design. So with these two values for SLS, ULS, you can start to compute and to make your constitutive law and to check if you can achieve the performance and the structural requirements of your specific project. This is also, this beam test is also connected to the performance class defined in the model code, the performance class for fiber reinforced concrete. For precast segment is typically a performance class 4C mini, which is recommended. So 4C means the number 4 means FR1 characteristic should be higher than 4 MPa. And the letter C means the ratio between FR3 and FR1 should be between 0.9 and 1.1. So this performance class could be defined by the designer according to the project requirements. 4C is considering as a minimum for precast segment. It could be 4C, it could be 5D, it could be 6E. This is based on the load take in account in the design. The designer defined this performance class, and after we do this beam test to check if with the concrete mix we use for the project and the type of dosage and the type of fiber and the dosage, we can achieve this value. So this means it's a very clear process. As we specify a concrete strength C50 after we do the cylinder or the cube to validate the compressive strength, we define the fiber reinforced concrete 5D, and we do the beam test to check if we can reach this performance with the type of fiber, the dosage, and the concrete mix used by the project. So material example, this is with typical drum mix for the 8060 BGP used in many precast segment projects. We do the beam test. In this case, we have done a 9 beam test. From the 9 beam test, we calculate the mean value. From the mean value, we calculate the characteristic value. To get the characteristic value, we apply the statistical method and the Studian coefficient, the standard deviation, which is very well described in the FIB Bulletin 83. And from this curve, we can observe that you have a clear hardening post-crack behavior. That means the residual strength after the first crack is even higher at FR1 as well as FR3. And the performance class, according to model code, is a 5E, for example. And this is using a typical mix for precast segment with a CM2 and 2 types of sand, crush aggregate, water, and steel fiber for TTG. Fiber reinforced concrete only solution needs to get this hardening post-crack behavior at the section level, means on the beam test. In fact, if you have a hardening behavior in bending at the sectional level, so beam test, this allows immediately structural ductility at ULS, cracking control at SLS. This is reason why it's really the minimum requirement to use fiber reinforced concrete only for precast segments. And this hardening post-crack behavior could be correlated more or less to the performance class 4C mini. Design by test is also a very common approach, where we keep always the material characterization on the beam test, but we move also on test scale 1. So two main tests, the bending test to simulate this load case, the behavior of the real segment under bending load. We can also check that the hardening post-crack behavior you get on your bead test, you will get as well on your real segment. And you can also, from this test, make some cracking monitoring. The second test scale 1 is the point load test. It's a way to simulate the concentrate load during the segment installation. Because when you install the segment, you know that you have to apply a high jack force pressure. And this could lead also some specific effort that we can simulate with this test. And we have done this test for many projects to better understand the crack pattern, to also observe that with fiber reinforced concrete, with the right dosage and type of fiber, you can control the crack less than 0.05 millimeter. And when you unload, the crack even reclose again. So this is also a way to bring some evidence, and to also it could be part of the quality control in some big projects. So, durability. Durability is certainly a key issue. Most of the projects are 120-year design life. Segment reinforced with steel fiber having a bending, hardening behavior contain cracks much thinner. And the fact to contain cracks, we get a positive effect on durability. So the durability is a complex topic. We can talk for the 2 days about that. Once again, I refer to the chapter 8 of the FIB Bulletin 83. There is two main aspects, the uncracking concrete and the cracking concrete. There is a clear consensus under the cracking concrete. Fiber reinforced concrete bring higher durability than rebars. Also, as well for the cracking concrete. The only point of discussion when we talk about cracking concrete is mainly the crack limitation. So there is different proposal in different standards. The main consensus today is proposed by the AFTES recommendation with some crack limitation according to the exposure class, taking account carbonation, chloride, and acid and chemical. When we talk about new development in the segmental lining design, what we have seen the recent years is the concrete mix and the concrete strength increase year after year, mainly due to the fast demolding necessity to boost the production process. Of course, if you have a higher concrete compressive strength, you need more steel to meet a non-brittle failure requirement. So it's the same, I would say, principle for reinforced concrete than for rebars. Considering that, we have continuously adapted our product to the type of mix design. We have to understand that the fiber reinforced concrete, it's a composite material. So we have to choose the right fiber for the right use in the specific mix to achieve a given performance. For everyone who know little about fiber reinforced concrete, that's quite easy. Just for you to keep in mind that the quality of the fiber is due to a combination of factors, the wire strength, the wire elongation, the shape, the length, the diameter, and also the LD ratio. LE ratio is saying something about the network and also the way the packaging of the fiber. So most of the case, we have a blue fiber to facilitate the mixing and also to guarantee good uniformity throughout the concrete. I say that we have the type of fiber to the compressive strength to avoid any risk of snapping. That means the fiber could break if the anchorage is too strong. The tensile strength of a steel fiber has to increase in parallel with the strength of its anchorage. Only in this way can the fiber resist to the force acting upon it. That's very important to keep in mind. That's why we develop different type of fiber with very optimized anchorage. We call that 4D, but we associate this anchorage to very high tensile strength to get an optimum way of working on of the fiber in the mix and to boost by this way the performance. An important point also is the network effect. It's important to have a minimum network. That means a minimum total length of fiber per cubic meter. From the empirical return of experience, this minimum network should be more than 10,000 linear meter per cubic meter. And you see that we know from a diameter of 0.75 to a diameter 0.8 or 0.9, that's could influence by 40% the fiber network. So this is where we are today. It's mainly with for precast segment with a fiber with a LE ratio 80, mean the length 60, a diameter 0.75, a very high tensile strength, 2,200 MPa, and the optimum hook to bring the best cost performance solution and to guarantee the class performance according to model code from 4C to 6E with a current dosage of 40 kg. Now let's move to the low carbon requirement, which is really a need for our world tomorrow. I just quote a UK engineer, Charles Allen. Concrete is recognized as the second most widely consumed commodity on the planet after water. It also contributes approximately to 8% of global carbon emission. And the main source of this emission is the manufacture of ordinary Portland cement. And when you know that in tunneling project, it is generally considered that 60% to 60 to 70% of embodied carbon is contained in the concrete lining itself. So that means all the industry need to make a great effort to improve the concrete lining and to move to low concrete lining solution by reducing or totally eliminate the use of cement, by decreasing the amount of steel, safe steel, less steel to safe steel with fiber reinforced concrete compared to rebars, and also to play with the total concrete consumption. So bye-bye concrete is not for tomorrow, but I think we are really enter in this transition period, and the industry is looking for low carbon lining. I just make a short history of all the big projects we have done in Middle East. I call that the breakthrough in Middle East. Middle East was very demanding in terms of durability. We start from the first project step in Abu Dhabi, it's a water gallery. You should know that in such environment, there is a very high chloride exposure. It's 12% chloride, so it's 4 or 5 times that the seawater. It's 5,000 milligrams sulfate, saying that durability was really a challenge. So to achieve the durability, the industry, and mainly led by Danish designer Cowie, try to upgrade the quality of the concrete mix by two actions. Use more high content of cementitious material as GBBS and fly ash, and also by using steel fiber. Doing that to meet the durability, we have also show that we can reduce the CO2 emission. That's why I say the lesson learned from all this project is that durability and sustainability goes hand in hand. All was made for durability, but in the meantime, we reached this CO2 emission reduction. Just one slide to illustrate this main trend. If we make a comparison of different embodied CO2 for different type of binder and steel reinforcement used for various bioinfrastructure projects, this is a slide also coming from Snowy. We see that the main gain is when you use GGBBS and fly ash, you can reach more than 75 CO2 reduction. And when you use steel and steel rebar, you can reach until 50% CO2 reduction. Just to give you some number, if Doha Metro have just 0.2 tons versus 0.7 ton of CO2 per cubic meter of concrete emission, compared to Copenhagen, that means that if Doha Metro will be built as a traditional solution, as Copenhagen, it will create more than 400,000 tons more of CO2 emission. So there is a good also synergy between the improvement in the mix design using more GBBS and fly ash or geopolymer and steel fiber. So this is the main trend, and we will not back to the previous design. One other project example is one we are currently doing in Paris. So the name is Grand Paris Express. It's a huge project because Paris authority try to create a new ring around Paris. That's why they call that the Great Paris. It's 200, altogether is 200 kilometers. The first lot was the Linear 16, and this lot was fully realized with fiber reinforced concrete only during the last 2 years. And it's about 20 kilometer excavation. The diameter is 8.7. The quantity of fiber is around 5,200 tons. You have 7 segments per ring. The concrete quality was a C50-40, and we use Ramix 8060 BGP with 40 kg per cubic meter. This project is very well documented. I can also share on this project many recent publications, the voice of the contractor, Eiffage, with a detailed return of experience, as they have done a very stringent monitoring on fiber reinforced concrete installed to measure the crack and all the aspects of the segment production. Once again, I have no time to go too much in details. I just give you some quote and the voice of the owner. Main message is less steel to save steel. So I quote the Grand Paris chair of the chair of the board of the Société du Grand Paris, Mr. Jean-François Montels, saying that our innovation policy is above all a level for making the Grand Paris Express a project in the service of ecological transition and developing practice in the world of public works. This is why we are oriented many of our projects toward sustainable design and construction, such as reducing concrete, choosing material, or even operating solution for the metro that consume less energy. That was the main vision. innovation have already given significant result. And one of the significant results is the use of fiber reinforced concrete for the construction of the segment of the Linéa 16. This is the first in France in underground work. Compared to reinforced concrete, fiber reinforced concrete notably represent saving of around 5,000 tons of steel for 10 kilometers of tunnel. And furthermore, in terms of resource, the fiber reinforced concrete can reduce the quantity of concrete by 2-3 centimeters segment thickness. In addition to the quantity of steel and concrete saved, fiber reinforced concrete also reduce the CO2 expenditure, both in cement factory and in steelworks. So it's about 10,000 tons of CO2 are saved on average of 10 kilometers of tunnel compared to rebars. Few words about another type of lining and the way we want to go is the permanent spray concrete lining. So this is not yet a standard solution as the fiber reinforced concrete for precast segment, but we see that also the market is moving from the traditional solution, temporary spray concrete, geotextile, and permanent cast in situ concrete to a permanent spray concrete lining. Some main design change driver are, of course, the robotization, the safety culture, the fact that we have also some spray waterproofing membrane available, the high performance technology of the fiber itself, the higher skill operative, the testing method, the fiber reinforced concrete material property, the quality control device, the improved design technique and standard, and the goal and to save also less concrete consumption and to have a less concrete consumption. The first main step will be to already consider the temporary lining as part of the final lining. Just doing that, we can also decrease the total consumption and the thickness of the final lining to give more value to the temporary lining. To give more value, we also need to collect more information, not only in the energy absorption, but also the residual strength to be able to get some value for service style, value for ULS, and to introduce this material property in the final design. Just to illustrate this, I just give you an example of a recent project in Australia. It's a WestConnex, and this project gets an award from the American Shotcrete Association. And this project uses permanent spray concrete lining with a high performance fiber to reach some value as FR1 3.4 MPa and FR4 3 MPa. This approach allows reduction in a tunnel support lining in order of 20%, and this diminution of concrete consumption also induce CO2 saving. This is also a good recent example of permanent spray concrete lining to move to low carbon lining. To conclude, I would just want to show you some recent development of what we call the ultra-low embodied carbon geopolymer concrete for tunneling segments. The EFC, Earth-Friendly Concrete, is a concrete with no Portland cement that has been developed by the Wagner Group in Australia. So such concrete is, we move from Portland cement-based binder system, including admixture, to geopolymer binder system, GBBS plus fly ash plus chemical plus admixture. All the rest remain the same, but with the EFC, you have no more Portland cement. Just some comparative analysis, the kilo CO2 equivalent. If you compare the Wagner EFC to the standard Australian OPC, you have a ratio almost from 1 to 10 when you calculate the CO2 saving. So it's very huge. They have investigate a research program has been conducted with this geopolymer concrete for segments. Some investigation concerning the fire resistance. So it's a fire test with the traditional fire curve according to the ZTV curve to compare different mix and to compare also the mix 3, which is the AFC concrete with 1.5 kg PP fiber and 35 kg Dramix 4D. And you see the surface material loss is very low. Is almost one of the best result in the different mix. Another type of investigation was also on the residual strength. This is a typical curve of the flexural tensile strength and the crack mouth opening displacement. And you see that even with a low dosage and 35 kg Dramix 4D, you get FR1 higher than 4 MPa and the FR3 higher than 5 MPa. So that means fiber could work positively with such concrete mix design in terms of structural requirements. And also there is some tests on marine exposure to evaluate the chloride ion ingress. And also, as you can see, the result with on the right of the column with the Wagner EFC is quite positive with 0.84 and 0.48 compared to the other mix is even much better. This product has been also tested and cast in different environments to check if we can cast properly, if we can cast according to the industrial process. So the main learning point with such geopolymer is provide an excellent long-term durability performance, exceeding that of Portland cement-based concrete. The compressive strength grade C50-60 can be produced consistently in segment manufacturing. The flexural strengths are comparable to those of Portland cement base. Excellent spalling resistance, excellent long-term durability, and of course, a reduction of the CO2. This such of product remain under investigation. We still do not have yet a big return of experience, but voilà. First result, first project showing that it makes sense to associate such type of geopolymer with fiber reinforced concrete. Concerning the product itself, you should know that for each type of fiber, now the producer needs to propose a EPD certification, environment product declaration. It's a way to communicate the key environmental performance indicator of the fiber product or Dramix over its lifetime. This is validated by an official independent third party, ITB, and this could be implemented in the LCA calculation. So we work also with One-Click LCA, which is an international society which helping us to calculate, you know, the carbon.
So final 2 minutes, sir.
Yes, I will finish.
Final 2 minutes. Last 2 minutes.
Last 2 minutes. Okay. And from the interrogation of the LCA result showed that the cradle to gate carbon impact of 1 kg of fiber production is about 0.88 kg CO2 equivalent. For comparison, 1 ton of steel produced worldwide emitted an average of 1.85 ton of carbon dioxide, just to give you a range. With this tool, with the EPD validated by independent body, with the One-Click LCA tool, we can also make some comparison of different solution, mixing concrete, rebar, and steel fiber, and showing that we can achieve this low carbon lining, mixing the GBBS plus fiber reinforced concrete. We work also on recyclable fiber. That's well, part of our DNA or R&D. And now let's move to the conclusion. As the chairman asked me to speed up a little the process, but I think we are just on time. So in conclusion, I would say that solutions for reducing CO2 emission and conserving resources are becoming increasingly sought after in the world of construction. So we cannot escape to this demand. And all the industry have to continue this research to allow this ecological transition period. It's a big challenge for the tuning industry. If we can improve the CO2 lining consumption, I think it will be a great step. And the second learning point is using Dramix FRC lining offer solution that allow clients to reduce their CO2 footprint by reducing the amount of steel, by reducing the concrete consumption, and by showing a good way of working with the new generation of geopolymer concrete. Well, that's all. So thank you.
Thank you, sir. Thank you for a nice presentation from Nirmana team. Any questions from audience? Just one question, any question? Okay, thank you, sir. Now I request Organized Committee Chairman Gururaj sir, Conference Chairman Gururaj sir to present a memento on as a token of appreciation virtually. It's virtually, sir. Afterwards, same thing will be sent through. Sir, they will focus.
Thank you very much.
Yeah, please. It's virtually.
Thank you very much for your invitation.
Once again, it's thanks from the Nirmana team 2022. Thank you, sir. Thank you.
Thank you. Bye-bye. All the
Bye-bye.
best.
Thank you, sir.
Good evening to all.
Good evening.
And do not
now,
hesitate to contact by mail if you need. Huh?
Thank you, sir. Now I request Organized Committee member, our Chairman, Mr. Madhukar, to take over the session, please.
We have a small bit of formality that we need to complete. Hello. Yeah, am I audible? Yeah. So we have a small bit of formality that we need to